The vibration measurement for washing machines. What you see is three positions in this diagram where we are going to take the vibration measurement. You see in the figure 9, we have a vertical axis, which you see at the 1, and then we have horizontal axis, which you see at positions at which we are going to do the measurement. And when we do the measurement, we are going to get the vibration measurements at various places. So what you see right now, I showed the diagram, basically talks about how we first facilitate to take the vibration measurement of washing machines, so that a normal washing machine which is running, how are the normal vibrations of those washing machines. And then when the washing machine is under the problem, what kind of vibrations would be there, what kind of AI model we will build to do that detection. Sometimes they call this anomaly detection also. But the net is that in order to extract the features of vibration, we need to decide what are the points we should take vibration in the predictive maintenance. It's a very important aspect. We need to understand that predictive maintenance does not only involve data science, it also involves the domain knowledge. That means the knowledge of washing machines and where exactly the vibrations occur. So my last episode, I showed you general working principles of a washing machine and where the vibrations occur on the washing machine. And then we also discussed, just to recap, that if the bearing of the drum of the washing machine is not working properly, what kind of sound we would hear. Now, here what we are going to do. We are not going to, for some time, don't think about what problem is occurring with your washing machine. You have to think about how you're going to capture the patterns which are going to detect if there is a problem with the washing machine. So that is what we are going to do now. These are the points which I am showing, where we are going to take the vibration, and then what kind of readings we would get. We would get something like, of course, we are going to capture the current also there, and then the vibration. And then we are also going to capture timestamp during which, the issue is occurring, right? Sorry, the vibration we are taking. And after we take these vibration measurements, we are slowly going to move towards data science. That is, we are going to talk about today what is standardization, that is standard scaling of the features. But let's, for now, understand what exactly is needed in, predictive maintenance. It is very important that we need to understand sometimes the machines, how they work in depth. Like, for example, if you talk of the Tesla machines have digital twin. What exactly digital twin means is that they do have a working, simulated, mathematical model of the car sitting inside the Tesla factory, which is also going to tell that what may happen in future for a particular Tesla car belonging to a particular person driving at a particular moment. So that's the digital twins. We are not going to talk about digital twins more in this. It is out of the scope of this video. We are going to talk about how do we take vibration measurements, how do we collect those samples of the vibration measurement, and then just do a pre-processing of that data. Why are we doing this? Because the AI models cannot take data which is non-standardized, right? And what features we need to extract depends upon your understanding of the machine. I'm extracting the vibration, which are features which are going to detect me to help predictive maintenance. And the vibrations, where and how we are taking, that's what we talked in this video. So keep your fingers crossed. We will go more depth about this, as we proceed. We're going to talk first, before we talk about washing machine vibration, what exactly is vibration, right? Because we are trying to tell here that we are going to make a measurement of vibrations inside a washing machine, and we are going to take all those vibrations, then as a data set, and we are going to extract the features, we're going to analyze, we're going to run through good vibrations which are having issues, train our AI model, to detect faulty vibrations, and ultimately where the fault is, developing and occurring, so that we can anticipate the fault in the washing machine using the AI model. So let's start with very simple definition of what's vibration. This spring is going to vibrate right? Back and forth. So this is a very simple definition of vibration, where vibration is occurring and it is also producing a sinusoidal wave, right? Now, this is a very simple definition which I'm trying to give of a vibration. In a washing machine, the drum is hanging, it's also rotating, and put on the it's resting on the springs, right? So it's resting on the springs. So now we will see a little explanation from curiosity of vibration.
Since the system behavior is defined by a single output, the x-coordinate of the mass, this is what's called a single degree of freedom model. We'll also
yes. Now this is a single degree of freedom model, and in washing machine we have multi-degree of freedom model, and we actually have to take measurements at several points inside a washing machine. We have to get all the readings of vibration, which we cannot do practically. It will become very complex. So we are going to take the reading at 2 points. But before that, let's understand some basics of how exactly vibration happens.
Neglect the effects of gravity. And for now, we'll assume that there's no damping, meaning that no energy is lost from the system as it vibrates by friction or other means. No external loads are acting on the system. The purpose of the model is to understand how the system behaves in free vibration, or in other words, how it will oscillate when it's displaced and then released. Since we've assumed there's no damping, the mass will continue to oscillate like this indefinitely. The way the system vibrates is defined by its equation of motion, which can be determined by applying Newton's second law. The second law states that the sum...
Exactly. So, I don't want to go more inside the basics. I can make this video more deep, but ultimately we have to make the sense of the vibration data. And when we make the sense of the vibration data, we will understand whether we are reaching our goal or not, right? The ultimate goal is to, anticipate fault. So the more we understand about the data, what we are dealing with, the data set vibration, the more we will be clear or have a clarity of what has to be achieved in the predictive maintenance here.
Sum of the forces acting on the point mass is equal to the product of its mass and its acceleration, F equals ma. We can figure out the sum of the forces acting on the mass by drawing a free body diagram. There is only one force, the force exerted by the spring, which is equal to the displacement x multiplied by the spring stiffness, k. And so, we obtain the equation of motion for the system. This is an ordinary differential equation, and the solution is a sinusoidal function.
Hold on, what we did here? Just want to stop here. Now we are trying to define the behavior of the spring using a mathematical equation. We started from Newton's law and now we got the sinusoidal. So how does sinusoidal equation help us to explain the behavior of the system? Let's see that.
T is time, phi is the phase angle, and A is the amplitude of vibration.
Perfect. Now this is the behavior of the ideal spring, right? But in reality, you do not get this kind of pure sinusoidal wave, because when the washing machine is working, you will get a random signal. You might get a pure sinusoidal wave for some time, and then the amplitude itself is decreasing. So that's what I'm trying to go from an ideal way to real world to make more sense of the data. But let's complete this.
We can determine A and phi by considering the initial position and velocity of the mass. Let's look at an example where the system has a mass of 5 kilograms and a spring stiffness of 20 newtons per meter, and a vibration is triggered by applying an upwards velocity of 2 centimeters per second to the mass. Since the displacement x is initially 0, the phase angle phi must also be equal to 0. And then we can differentiate the equation for x to calculate the amplitude of vibration A. An important property that can be calculated from a mass spring model is the system's natural frequency, the frequency at which it will oscillate naturally when in free vibration. It's given by this term in the equation of motion, and is denoted using the Greek letter omega. It depends only on the mass and the spring stiffness, so no matter what the initial conditions are, a system will always oscillate at the same frequency. It has units of radians per second, so is called the angular natural frequency. But it's sometimes more practical to think of the natural frequency as a number of cycles per second, in which case it's denoted using the letter f and has units of hertz. The inverse of the natural frequency is the period t, which is the duration of each cycle in seconds.
So we are dealing with the frequency data set now. I think it should be clear what we are by frequency here. Frequency is simply the number of occurrence of that event, right? What is that event? The event is the oscillation of the spring. How are we expressing the oscillation of the spring? By x displacement in z time also. This keeps on happening. So let's say if it is 50 hertz, then it's occurring 50 times, right? That's what is being explained now.
Let's compare how two different systems oscillate. Both of these models have the same spring stiffness, but different masses, and so different natural frequencies. The heavier mass oscillates at a much lower frequency.
Why I am showing this to you? Because we have a drum in the washing machine, which is rotating. It has certain mass. We also have not only the drum, we also have the pulley as well as the belt tied to the motor, which are going to have different mass. Which means, let's see the simplest one.
A neat demonstration of the natural frequency is the tuning fork. When the fork is struck, it vibrates at its natural frequency, which is much faster than shown here. This causes the air molecules to vibrate at the same frequency, which produces a corresponding tone. By assuming that the prongs behave like cantilever beams in bending, beam theory can be used to derive a formula for the natural frequency of the fork. The density, length, and cross-section of the prongs can be calibrated to obtain the desired tone. Of course, when a mass oscillates freely, it doesn't do so indefinitely. Energy within the system is dissipated as heat over time, so the oscillations progressively decrease in magnitude and eventually stop altogether. This loss of energy is called damping, and it occurs in all real mechanical systems. There are several different mechanisms.
We are using damping for our advantage. That means that we have something like shock absorbers when the drum is rotating. Why do we put those? Because it should be able to absorb the motion. And finally damp it so that what is desired is rotation of the drum, not vibration of the drum for the washing machine. But we are using the as for example, when we drive the car, we are expecting the car to move forward, but we also have the springs in the tire which will absorb the ups and downs or the humps of the road to make our the travel smooth, and ultimately they damp it. So that's what we are using for our advantage, damping.
That can contribute to the overall damping of a system. With structural damping, energy in a vibrating structure is dissipated due to the relative motion of components at structural joints. And material damping is damping provided by the material itself, where energy dissipates in a vibrating material due to interactions occurring at the molecular level. To improve our spring mass model, we can lump the damping from all of the different sources together and represent them by a single damping device called a will oscillate, and the magnitude of each successive oscillation will decrease until it stops.
So this is the kind
if the damping of the system is increased significantly, which you can think of as the dash.
So this is the kind of waveforms we are going to get. All different kind of waveforms. So we are going to finally deal with a very complex waveform.
Being filled with a far more viscous fluid. Any oscillation will be completely suppressed by the damping. This is called an overdamped system. And a critically damped system occurs right at the limit between these two cases. It is just enough damping to suppress vibration. Each of these cases has a different function that defines the displacement of the system, obtained by solving the equation of motion. The ratio of the actual damping coefficient of the system to the damping.
We're not going to go more into mathematics of this. It's just for understanding. So you want to push this. Let's go further.
This type of loading often occurs in rotating machinery. A common problem with turbines and motors occurs when a rotating component is unbalanced, meaning that its mass is unevenly distributed.
Here we go. Now we come to the real problem that we have a drum which is rotating. Now, the vibration starts occurring when we have unbalance in the load. That's what is been explained now.
This introduces a load that has a sinusoidal component in the vertical direction and can cause vibration. Unbalance can occur because components were poorly fabricated or have been distorted. But eccentric masses are sometimes added to motors on purpose. Intentionally unbalanced motors are how phones and video game controllers are able to vibrate. We can analyze this type of forced vibration using the spring and dashpot model by adding a sinusoidal external load. The resulting equation of motion is similar to the free vibration case, but is a non-homogeneous differential equation. Its solution is the sum of two functions, a complementary solution and a particular solution. The complementary solution is the solution to the homogeneous, and if the system has very little damping.
This is the way
the masses in the model has its own equation of motion.
We saw the different vibrations. Let's come back to have some simulation of model. All we saw now was the vibration. We are not getting into any of the equations or mathematics right now. Right now, you just have to understand that vibration is. So we have the model wherein we are seeing the rotating of this machine. And this drum is, you see that this whole drum is being rotated by a motor which is below this. But at the same time, this drum does not perfectly rotate on the vertical axis. It might have, when it's rotating, it might have a sidewards motion. These springs absorb that sideward motion. You need to realize that. And when such a thing happens, it is going to have a vibration. That is the vibration we're going to measure here. It is the uploading washing machine. We are going to see front loading washing machine. Now, here we see now is that drum is rotating, and backside is your motor, right? But the drum does not perfectly rotate on vertical axis. It keeps on shaking, right? This shaking is the vibration which you're measuring. You see this, the cloth, and see the motion here, right? It is hanging on the springs. So this is what we are going to study, these vibration signals. So this is now a simulation. It's actually a 3D animation of how, this is your front loading washing machine. So now they are showing how the water flows inside the drum. Now this is the way, the flow of the water is there inside the drum. You see this, the drum is rotating, and this is your front loading washing machine. There you go. So this is the way it vibrates. So let's see a more simple explanation of vibration by one more person. So now we are going to see the Kaggle data sets, and we're going to go and get the vibration data for washing machine. So just type vibration washing machine, then go to a point where you start seeing the data set. This is your smart data set. And what I did is that I went here, and then I saw the different details here. We are going to go more deep into this data set as we progress. But for now, you just have to understand that our washing machine model and what all we discuss right now. There is a vibration data set which we'll extract, and then we'll start working on that. If you see this data, I'm going to give a quick introduction to this data. There's two types of data here. There is one is data which is fast.csv, and the other data is slow.csv. In the fast.csv, we have something like as vibration, current, and the Unix timestamp. This is the thing. Now, such kind of data sets, there are a lot of samples. I will also discuss in my next episode about samples. That means how many samples should we take to train our AI model effectively so that you give a new washing machine, it accurately detects, you give any other washing, not new washing, any other washing machine, any other model, washing machine, or or somewhat at least bit similar like front loading washing machine. Would you be able to detect the fault? So if you train your AI model very well, yes, you'll be able to do that. But for now, we are going to focus more on vibration. Yeah, this data set also has slow.csv, which is again, having huge data, a lot of data. There is a metadata about this. You can see here. The metadata explains what the data contains. The only thing what I could find, I was falling short of was the units of measurement, which we'll later discuss about it. This is the metadata what you're talking about: timestamp, device ID, brand, model, program, temperature, spin, load, failure, observations, those kind of things. We wanted to have a look at this data set. I took this data set, and now what you see is this is a program which has been given with the data set. Now I said that we wanted to have a standard scalar dot fit transform, right? So this is the data set what I'm taking.
And in the data set, we do have, you know, some features which I need to discuss. In the data set, what I downloaded is smart PDM data set here. In the smart PDM data set, we have data for fridges and code also. Fridges we are not going to consider. We're going to consider washing machines. And in the washing machines, we have this individual data sets, which I was talking about two data sets there, which is one is fast and one is slow. We're going to refer the fast one. So as soon as you open this fast data set, you will see that you know you have a Unix timestamp and you know and a vibration data. So let me open this. I'm opening this. I say okay. Sorry, you have both Unix timestamp, current, and vibration. That's what you saw. Now, what we are going to do is that when we do a feature extraction, data science, that means we are going to extract the related features using all these measurements. Uh, like you have the vibration data. Now, what exactly mean by feature extraction? So I will not speak first the data science language. I'll speak in a very simple terms is that feature extraction means, say for example, you are driving a car, right? And you want to see, that if the car can stop due to some fault, right? So you want to predict the fault. Then what would you do is that you would take main features like, what speed the car was driving, what was the acceleration, what was the direction. Those are the main measurements which you would be interested if you want to calculate if there is a fault going to occur in the vehicle and it's going to stop. Similarly, here in the washing machine, we are going to extract the features of the washing machine, the measurements which we are interested, which can help us in the fault detection. So that's called as feature extraction in a very simple language. So that's about the fast CSV, and you can see here that I am referring the extracted features.csv here. And as I told in the beginning of the episode that we're going to apply a standard scaler to fit transform to get the standardized features. So let me go a little deep into the program first. So what we do here is that we open this as a CSV file, and then we fix our separator. This is our separator for the data, right? And then there is a NEM data. That means it may be blank or null. So I'm just replacing this for time being by 0, just for explanation's sake. We will deal more with this in our next episode. And then I'm going to, uh, go in the next instructions. So we read the data, then we are extracting X columns, then we are extracting the values, and then we are putting a standard scale. What's the standard scaler? Now I'm getting more into data science. Until now, I was more into the domain. One thing is very, very important when we deal with, especially predictive maintenance. You need to have a perfect domain knowledge, top level domain knowledge of, say, mechanical engineering, right? And on top of that, what machine you are dealing, you should have a complete domain knowledge of that machine. These are the two necessary things, we need, to achieve predictive maintenance. Otherwise, it's just not possible with knowledge of data science. But that does not mean that, uh, you know, you can just work without knowledge of data science. Data science is also needed, need in-depth knowledge of data science also. So let me explain you what's a standard scaler, right? And then we'll try to end our episode. We'll start with the next episode. So why do we need standard scaling? How you need to perform scaling on the feature data? that we should see first. But before that, I was showing the data set where you have the individual data set as well as you have feature data set. So let's go here. As you see my screen, um, I'm into the smart PDM data set. Then you have two washing machines, and then you have WM extracted features, right? So this is the just what I'm talking about. Uh, you have all the values here. These values which are extracted, the feature values which are extracted, these needs to be standardized. You have vibration values here uh, for different axes, as well as you have current as well as power factor, but we are going to focus on vibration. But before that, let's see why we need to standardize. The first very important thing we need to remember is that our AI model we are going to build using the non-ensemble methods. That is, you will use logistic regression method. What is logistic regression method? I'm not going to talk right now, but what I'm telling is that right now I have thought of a method as logistic regression because we are going to focus on a very important part of the machine, that is bearing, which uses logistic regression, to detect the bearing faults. So I'm going to select logistic regression. For that, we need to do feature scaling. So let's see the video now, what they talked about in this video for the feature scaling.
Hello all, my name is Krish Nayak and welcome to my YouTube channel. Today we'll be discussing why do we require feature scaling. Whenever we are solving any machine learning use case or deep learning use case, why do we require to perform feature scaling with respect to the data set that we have? So remember guys, whenever we are discussing about feature scaling, that basically means we are discussing about features, right? Now suppose let me consider that in my data set I have features like height, okay? I have features like weight. And suppose based on this, right, I want to predict what is my body mass index, suppose my BMI, okay. Now suppose in this case, what it may happen that my height and weight are basically my independent features and my BMI is basically my dependent feature. Suppose this, I'm just taking as an example. Now remember guys, every feature has two things, okay. One is, I'm just talking about the values inside this, okay. Whenever I'm talking about this particular values, this values has two things. One is, it is represented by magnitudes.
If you're a person who's fairly good with numbers and logic, did you know that you can make $70,000 a year or more as a...
And then it is represented by units, okay. Because we will be using these features, we'll be actually recording this observation based on the magnitudes and units. Now if I take an example of height, I'm computing height by centimeters. Suppose I'm computing it, okay. So this centimeters is basically my units. And the value inside this height is basically my magnitude. So it may be 180 centimeters, 170 centimeters. So this value is basically magnitudes, right. Now similarly, if I take weight, my unit may be kg, okay, because that is how we actually calculate weights. Then if I want to put some values like 78, it may be 84, okay, and these are my magnitudes. Now if we don't perform feature scaling, what may happen in this scenario is that some of the machine learning algorithms, okay, we'll discuss about some of the machine learning algorithms where we have to compulsorily do feature scaling. Now if I am going to take this particular magnitude values and try to apply in some machine learning algorithm, just let me take an example like k nearest neighbor. Now you know that k nearest neighbor works on Euclidean distance, okay. Now remember, if I take this same magnitude and if I try to plot this in a two-dimensional graph, right, so this point may be it may have various like varying distances and the distances will be huge, because here I am basically going to use Euclidean distance. So what we have to do is that we have to scale down this value, guys. We have to scale down these values in such a way that each and every feature that we have will try to perform some type of scaling techniques. I have already discussed what are the different types of feature scaling in my previous videos, but we are just trying to understand why feature scaling is required. Understand guys, this value differ a lot. Okay, and when we are using some of the algorithms like KNN, where the Euclidean distance is very important, and that Euclidean distance is computed based on this particular magnitude of the value. So we should try to perform scaling, and we should try to scale down these features. And our scaling also happens with respect to that specific features only. So suppose if I am scaling this between 0 to 1, okay, I may call it as a uniform scaling or min-max scaling. I may also scale this based on the standard normal distribution. I'll call it as standard scalar scaling. So all the different types of scaling are there. And if you have not seen that video, please go and watch that particular video. Different types of scaling techniques. Now, let me just make you sure why we require scaling and which all algorithm will be requiring scaling. And it is always necessary that you perform scaling in those algorithms. So the first algorithm that I would like to consider is your linear regression. Now remember guys, in linear regression, this basically works, and the coefficients in linear regression is basically found out with the help of gradient descent. And always remember, my values of my, the coefficient should be able to converge at this particular global minima. It should be converging in this global minima. Now remember, if we perform scaling, then it may happen in such a way that already the initial randomly initialized coefficient may be very, very near to the global minima. If I don't scale it, then it may happen in such a scenario that my random initial point of the coefficient may be far away. Okay, but always remember, if we scale down this value, how convergence will happen quickly. Okay, how convergence will basically happen quickly when we are performing scaling in case of linear regression. Now always remember, after this, suppose if we have some of the machine learning algorithms both in supervised and unsupervised technique wherein we are specifically using Euclidean distance, okay, like k-means clustering, like k nearest neighbor, right? So in this kind of algorithms we use Euclidean distance. And again remember guys, if we don't scale down this value, what may happen? We'll be having a huge distance over there. So we should try to scale down that value and try to perform and try to give this feature scaled in this k-means or k-n algorithm, so that our algorithm will run very, very faster. Okay, and always remember guys, this particular technique, this is an unsupervised technique, k-means clustering, it may be hierarchical mean clustering. So wherever, whichever algorithm this kind of stuff is there, wherein you have gradient descent concept or you have Euclidean distance concept, at that time you should basically prefer using feature scaling. Okay, and similarly this applies to deep learning also. Now you know that in each and every deep learning technique, gradient descent will come into picture, right? So there it is very, very much compulsory. I'm talking about both CNN, ANN or RNN. It is very, very much compulsory to do the feature scaling. Now for CNN, where your inputs are basically images, the type of scaling that is basically applied is called as unit scaling, wherein your pixels between 0 to 255 for that particular images will be converted between 0 to 1. Okay, and that is basically called as unit scaling. And so these were the basic things about this. But when should we not apply feature scaling? That is also very, very important, right? So I'd like to specify some of the algorithms where you don't have to use feature scaling, and it is not necessary, because if you perform feature scaling, then also it is not going to make such impact. So some of the algorithms like decision tree, random forest, XGBoost. So these are basically my ensemble techniques, right? In all these techniques, you don't have to use feature scaling, guys, because just understand, decision trees will just be creating trees, right, based on the features, based on these features. So if you scale down this value, it is not going to make that particular impact, because the number of branches will be almost same, whether you do the scaling, whether you don't do the scaling. So you do not have to perform. And you know that random forest is also an ensemble technique, and within that you will also be using decision tree. Similarly in the case of XGBoost. So you don't have to perform specifically some feature scaling in this particular case. Let it be a regression problem, let it be a classification problem. So I hope you got a basic idea why and when to perform feature scaling, what are the necessary conditions, which all algorithms you will prefer performing feature scaling.
So this is the reason why we need the feature scaling here. And Let's see some example, some more deep example of this.